Welcome to the Deep Dive, where we take a stack of sources and unpack the most important insights just for you. Today, we're plunging into a really exciting space,
Hmm.
how artificial intelligence is starting to fundamentally change cancer care, particularly within pathology and oncology labs.
Yeah, it's a fascinating topic, and the source leading our deep dive today is this comprehensive review. It pulls together insights from experts representing the European Society for Medical Oncology, ESMO, and, well, a whole host of international specialists.
Right.
They've looked at where AI stands right now in this field and, where it's clearly headed.
So our mission today is to understand the practical reality. How is AI being used today in cancer pathology? What incredible opportunities is it unlocking? What are the real-world hurdles preventing wider adoption? And, well, what does the near future look like for AI in diagnosing and treating cancer?
It's a field moving so quickly, isn't it? And this review gives us a really solid look at the current state and, frankly, the immense potential.
All right, let's unpack this then. When we talk about AI in this context, I mean, it's a branch of computer science using machine-based approaches to emulate human intelligence, right? Often for making predictions or decisions. But the source gets into some specifics about the types of AI most relevant here.
That's right. Yeah. At the heart of many of these applications is machine learning, or ML. This is where algorithms learn patterns directly from data without needing explicit programming for, every single possibility.
Okay.
And a key subset of ML is deep learning, or DL.
And deep learning uses neural networks, right? That's the core idea.
Precisely. Artificial neural networks, or ANNs, they're models sort of loosely inspired by the structure of the brain, with layers of interconnected neurons. Deep learning uses deep neural networks, or DNNs, which have, well, many hidden layers.
Lots of layers.
Lots of layers. And this allows them to learn incredibly complex, sort of hierarchical patterns from the data.
Okay, so deep learning is essentially complex pattern recognition, especially useful when you have all those layers to find really subtle connections.
Exactly. And for processing images, which is absolutely fundamental in pathology, a specialized type of ANN called a convolutional neural network, or CNN, is key.
CNNs?
Yeah, CNNs are built to process visual data exceptionally well. They identify features from simple edges to really complex textures and shapes. The source actually notes that in this field, AI and DL are often used almost interchangeably because DL, particularly with CNNs, drives so many of the advances.
That makes perfect sense when you think about analyzing those complex tissue slides.
Mm.
It's all visual,
Hmm.
and these models learn in different ways. I think the review mentioned that.
Yes, yeah, it touches on the main training frameworks. Supervised learning is probably the most common.
Mm-hmm.
You feed the model labeled data, like images clearly marked cancer or not cancer, so it learns to classify new, unlabeled data.
Got to give it the answers first.
Pretty much. Then there's unsupervised learning, which finds patterns in unlabeled data that's useful for clustering or discovering hidden structures you didn't even know were there. Semi-supervised learning is kind of a mix of the two. And then you have generative models, like GANs, which can actually create new data that's similar to the training data, though they're maybe less central to the diagnostic applications we'll focus on today.
Got it. So armed with that understanding of the tech, let's dive into what AI can actually do in cancer pathology and oncology right now, what's happening on the ground.
Right. The application of AI holds, truly enormous promise to really transform these fields. We're seeing potential for automating time-consuming tasks, significantly improving the accuracy of detection and classification, gaining deeper insights into the tumor microenvironment,
Yeah.
and crucially, enhancing our ability to predict how a patient's cancer might behave and respond to therapy.
So automating, enhancing, understanding, and predicting. Lots going on. Let's start with something fundamental, cancer detection and classification. Pathologists spend hours, days, manually reviewing slides. How does AI impact that?
Well, AI aims to streamline this really labor-intensive process, reduce that subjective variation you can sometimes get between pathologists, and provide more consistent, standardized results.
More objective.
Exactly. By training algorithms on huge data sets of slides meticulously annotated by experts, mind you, they learn to spot and classify cancer cells, assess tumor grades and stages, identify microscopic features. These tools can act almost like a second pair of eyes for pathologists, augmenting their workflow or, in some cases, automate initial screening steps.
And the review looked at quite a few studies on this,
They
right?
did, yeah. 68 studies focusing just on detection and classification. Most aimed at identifying neoplastic areas, the cancerous bits classifying lesions as benign or malignant, and determining specific diagnoses or grades.
Makes sense.
And studies on common cancers like breast, prostate, and lung were frequent, simply because, well, there's more data available for training in those areas.
Okay, and here's where it gets really interesting. I remember reading about a specific challenge, a competition, that highlighted the potential here.
Ah, yes, you must mean the Chameleon 16 challenge.
That's a one.
Yeah, this was a competition assessing how well deep learning algorithms could detect metastatic breast cancer in lymph node whole slide images. The results were genuinely impressive.
How so?
The top AI algorithms performed comparably to pathologists who had unlimited time, and perhaps even more strikingly, they performed better than pathologists working under typical time constraints.
Wow, so AI didn't just match human performance, it actually showed robustness under pressure. That really hints at a real ability to boost both accuracy and efficiency in busy labs.
Exactly. It was seen as a bit of a watershed moment, really, and the source highlights specific examples too, like in prostate cancer, where assessing the Gleason score is absolutely critical. DL algorithms showed really robust performance there, with a median AUC of 0.9.
AUC, maybe quickly explain that for listeners less familiar with these metrics.
Sure, AUC stands for area under the curve. You can think of it as a measure of how well a model can distinguish between two groups like, say, cancer versus not cancer. An AUC of 0.5 is basically random chance, like flipping a coin,
Okay.
while 1.0 is perfect distinction. So an AUC of 0.9 is very, very good. It means the model is excellent at telling the difference.
Got it. Very high accuracy. And the review mentioned one prostate cancer system with a high Cohen's kappa. What's that tell us?
Yes, a Cohen's kappa of 0.92 with expert pathologists. Kappa is a statistic that measures agreement between different raters in this case, an AI and a human expert beyond what you'd expect just by chance. So a kappa of 0.92 indicates extremely high agreement. The AI's grading aligned remarkably well with the expert consensus.
That's really solid validation then. And what about looking across many cancer types at once? Pan-cancer studies.
Ah, yeah, the pan-cancer studies are fascinating. One CNN-based analysis accurately classified over 17,000 whole slide images spanning 28 different tumor types and 14 normal tissues with an AUC of 0.98.
Wow, 0.98 again.
Yeah, exceptionally high performance. It's just classifying where the tissue came from.
But the real surprise from that pan-cancer work wasn't just classification, it was connecting the images to genetics, right?
Absolutely. That was the pan-cancer computational histopathology analysis, or PCGP. It went further. It correlated histological patterns seen in the images with specific genetic alterations like whole genome duplication, WGD, and copy number alterations, CNAs.
Oh, hang on. You're saying the AI was seeing something in the picture of the tissue, the H&E slide, that lined up with changes in the patient's DNA. How is that even possible?
Well, it suggests there are subtle, observable morphological traits, maybe in cell shape, tissue texture, the arrangement of cells, the surrounding environment, that are direct or indirect visual manifestations of underlying genetic changes.
Things we just don't normally see.
Exactly. AI, particularly deep learning, seems able to pick up on these incredibly complex genotype-phenotype associations that are often invisible to the human eye or, traditional analysis methods.
That's pretty mind-bending. It implies that these standard slides, the ones pathologists have used for decades, actually contain genetic information encoded in their appearance that we just haven't been able to read before AI.
That's exactly the implication, and the potential here is enormous. Now, it's important to say these tools aren't yet validated to replace genetic testing. Their performance is still variable for specific mutations,
Okay.
but they could be incredibly useful for triaging, helping decide which patients are most likely to have a specific mutation and should maybe be prioritized for genomic sequencing, especially in settings where universal testing isn't feasible or affordable.
A screening tool for genetic testing almost.
Sort of, yeah. Or a prioritization tool. And it's not just DNA. The source also mentions predicting gene expression from images.
Yes.
AI models have shown they can predict transcriptomic subtypes, these patterns of gene activity, and even infer spatial variations in gene expression across a tissue sample, all directly from standard H&E images. This opens up possibilities for much quicker, perhaps more affordable ways to assess certain molecular markers that currently require more complex and expensive lab techniques.
Okay, so moving beyond detection and these incredible biomarker predictions, AI is also being applied to predict something incredibly important to patients,
Yeah.
their outcome. How does AI help assess prognosis?
Right, prognostic models. These use AI to analyze combinations of data, could be clinical information, imaging data, sometimes molecular profiles to generate personalized risk assessments for the patient.
Okay.
They can predict the likelihood of things like disease recurrence, metastasis, or overall survival. And these predictions can really help guide clinicians and patients in making informed decisions about treatment plans, follow-up intensity, things like that.
And the review identified quite a few studies focused on this area too.
They did. They found 92 studies using AI on whole slide images specifically for prognosis. Again, largely in common cancers, breast, prostate, colorectal melanoma, likely due to data availability. But some studies showed really remarkable performance.
Give us an example. What stood out?
Well, there was a CNN called Mesonet developed for pleural mesothelioma. It actually outperformed conventional clinical models for survival prediction.
Better than the standard methods.
Yes. And what was particularly interesting was that it identified predictive features within the image that hadn't been previously known or associated with outcome through traditional pathological analysis.
So the AI wasn't just modeling the factors we already know are important. It was actually discovering potential new biological markers for prognosis just by looking at the slides.
That's the implication, yes. It's finding patterns linked to outcome that humans hadn't recognized. Another striking example was a deep learning algorithm predicting cancer-specific survival in early colorectal cancer based solely on morphology, just the appearance of the cells, and it achieved a hazard ratio of 3.04.
A hazard ratio of 3.04. What does that mean in practical terms for a patient?
A hazard ratio compares the risk of an event, in this case, dying from the cancer happening in one group compared to another. So a hazard ratio of 3.04 suggested that patients whose tumors had certain morphological features identified only by the AI were over 3 times more likely to die from their cancer compared to those without those features.
Based purely on the image analysis.
Based purely on the image analysis, it really highlights AI's potential to spot these high-risk morphological patterns that might otherwise be missed.
And this isn't just for common cancers. What about rare ones where data is usually limited?
That's a great point. The source mentions AI showing promise even with limited data in some rare tumors. For example, predicting metastasis risk in pancreatic neuroendocrine tumors, or discriminating high versus low risk rhabdomyosarcoma. Identifying these risk groups early is crucial for treatment planning in those diseases.
That potential to unlock insights even in less common diseases feels huge. But the review highlights something else quite strongly, that while image analysis alone is powerful, bringing in more types of data seems to make AI even stronger.
Yes, this is a major theme running through the research. The power of multimodal data. Combining different data types, so pathology images, yes, but also clinical records, genomic data, transcriptomic data, even radiology images like CT or MRI scans into a single machine learning model consistently seems to outperform models based on just one data type.
It's like getting a more complete 3D picture of the cancer instead of just looking at one flat slide.
Exactly. That's a great analogy. Each data type offers a different perspective, a different layer of information. By integrating them, AI can potentially find complex relationships and predictive signals that aren't visible in any single source alone.
Any examples of that showing real benefit?
Yes, the source cites few, like an integrated model for predicting breast cancer therapy response that combined clinical, pathology, genomic, and transcriptomic data. It achieved an AUC of 0.87 and did significantly better than models using just one of those features. Another one integrated radiology, histology, and genomics to predict response to PD-L1 immunotherapy. That model hit an AUC of 0.8 and clearly outperformed traditional single markers like tumor mutational burden, TMB, which had an AUC around 0.61, or just looking at PD-L1 IHC staining, which was around 0.73.
Right, TMB being the total number of mutations in the tumor, and IHC is that common staining technique pathologists use to look for protein expression.
Correct. So the multimodal approach is leveraging the complementary information from these different layers of biological and clinical data. The big challenge here, as you might guess, is actually getting large data sets where all these different types of data imaging, genomics, clinical outcomes are available and linked for the same large group of patients. That's not easy.
Right, the data challenge again. So, okay, we've talked about all this incredible potential spotting cancer better, predicting mutations from images, forecasting outcomes, integrating all this data. Why isn't AI completely ubiquitous in cancer labs and clinics right now? What are the roadblocks?
Yeah, the review is very clear on this. Despite the rapid progress, there are still significant hurdles to overcome before we see routine clinical implementation. They kind of group them into several categories.
Let's walk through them. What's a big one? Culture, maybe?
Conceptual and cultural barriers are definitely significant. There's often a natural resistance to adopting radically new technologies in established fields like medicine. Clinicians might, consciously or unconsciously, fear being replaced or perhaps feel their expertise is being devalued.
The black box problem, too.
Exactly. There's also that black box perception, a reluctance to fully trust or delegate crucial decisions to an AI model whose internal workings aren't always transparent or easily explainable. In medicine, understanding why a decision is being recommended is often just as critical as the recommendation itself.
That makes total sense. Trust is absolutely paramount. What about technical challenges? Things that can go wrong with the tech itself.
Technical variability is a major one. Subtle differences in how tissue samples are processed, things like fixation methods, staining quality, even the thickness of the tissue slice, or inconsistencies between different digital slide scanners, can all introduce biases that might affect how an AI model performs.
Garbage in, garbage out, potentially.
To some extent, yes, and computationally, there's always the risk of overfitting. That's where the model learns noise or idiosyncrasies specific to the training data rather than generalizable biological patterns. And of course, the issue of biased training data sets potentially just reflecting and amplifying existing biases in healthcare.
And data itself, just getting enough of the right kind, continues to be a barrier,
Yeah,
even though it's the fuel for AI.
absolutely. Training these sophisticated models requires enormous quantities of high-quality data, specifically those whole slide images with accurate and really detailed annotations. Acquiring and curating these large, well-annotated data sets is incredibly time-consuming and expensive. It's particularly challenging, the review notes, for developing robust predictive biomarkers, which ideally need data linked to outcomes from large prospective clinical trials.
Is it also tricky just deciding which AI approach is best for a given problem? Like which algorithm to use?
Yeah, the source admits that choosing the optimal deep learning algorithm or architecture for a specific task is still an active area of research and debate among experts. Different approaches have different strengths and weaknesses. They might require different data types or levels of annotation, and they vary in computational requirements too. There isn't always one clear best choice.
And maybe the most critical hurdle for widespread clinical use, validation, proving it actually works reliably.
This is arguably the most significant barrier right now. For any diagnostic or predictive tool to be routinely used in clinical practice, it needs rigorous validation demonstrating its accuracy and its clinical utility. Often this requires the highest levels of EVARs, like level IA or IB from clinical trials.
And where are we with that for AI in pathology?
The review points out quite starkly that currently, no prognostic or predictive AI biomarkers in cancer pathology have met this highest standard of evidence.
Wow. Okay, so lots of exciting research results, maybe promising pilot studies, but proving it works consistently and actually improves patient care in the real world day in and day out. That's a whole other ballgame.
Exactly. And the required level of validation also differs depending on what the tool is supposed to do. A simple screening tool might need less stringent evidence than, say, a tool that's directly guiding personalized therapy decisions where the stakes are higher.
Makes sense. Finally, what about the regulatory and financial challenges, the practical stuff?
Yeah, those are real too. The regulatory pathways for approving complex AI algorithms in medicine are still evolving, and they vary by region. The FDA in the US has its approach, processes in the EU might differ. There's ongoing debate about how best to regulate algorithms that can potentially learn and change over time after they're deployed. And financially, the upfront investment for the digital pathology infrastructure, the scanners, the massive data storage, the high-performance computing needed that can be substantial, especially for smaller hospitals or labs.
A barrier to entry.
It can be. However, the source does note that once that infrastructure is in place, the marginal cost of deploying and running additional AI algorithms is often relatively modest, which could be a significant advantage in the long run.
Okay, so serious challenges across the board: cultural, technical, data, validation, regulatory, financial. But despite all of them, the review points to some concrete signs of progress tools that have actually cleared some of these regulatory hurdles.
That's encouraging, yes. It shows it's possible.
Huh?
Some AI-powered tools are starting to receive regulatory clearance, which indicates they've met certain performance and safety standards, at least for specific uses.
Like what?
In the US, the FDA authorized Page Prostate Detect back in 2021. This tool is designed specifically to help pathologists identify suspicious areas on prostate biopsies when they're reviewing slides.
And did it demonstrate a benefit in the studies?
Yes, the authorization was supported by data showing it improved both sensitivity and specificity for cancer detection. Notably, it led to an average 70% reduction in false negative diagnoses in the study.
70% reduction in missed cancers. That's a significant potential clinical impact.
It is. It suggests it can act as a valuable safety net or second check.
What about in Europe? Are there similar examples?
Yes, in the EU, AI tools have also gained some ground. For example, there's Okindix or Lapse Risk BC. That's an AI tool using whole slide images to help predict the risk of relapse in certain types of early stage breast cancer.
Okay.
And another one, Okindix MSN2 at CRC, is designed to help pathologists pre-screen colorectal cancer slides for features associated with microsatellite instability, or MSI.
Which is important for guiding immunotherapy decisions, right?
Exactly. So these tools are starting to emerge, aiming to integrate AI into clinical workflows to improve efficiency or risk stratification or diagnostic accuracy. However, the review does add a caveat that despite these approvals, the widespread adoption of these specific tools in daily practice is still somewhat limited. It suggests there's still a need for more real-world evaluation, integration into existing lab systems, and maybe building more clinician confidence.
So approval is one step, but getting it widely used is another. Makes sense. Looking ahead then, the field is clearly not standing still. What novel approaches and future directions does the source highlight? Where is this all going?
Oh, the future looks very dynamic. Novel deep learning architectures are constantly emerging. Transformers, for instance, they were originally incredibly successful in language processing, like with GPT models. Well, they're proving highly adaptable to image data as well and showing a lot of promise in pathology.
Interesting. And there's a lot of buzz around foundation models. What are those exactly in this context?
Yeah, this is a really significant trend, I think. Foundation models are these massive AI models trained on enormous, incredibly diverse datasets. The source mentions models trained on hundreds of thousands, even over 1 million whole slide images from various sources.
Wow, 1 million slides.
Huge scale. The idea is they learn incredibly generalizable representations of tissue morphology from this vast data. These pre-trained models can then be quickly adapted or fine-tuned to specific downstream tasks like detecting a particular cancer type or predicting a specific mutation with much less task-specific labeled data required than starting from scratch.
Okay, so it's like building a super knowledgeable base AI that already understands pathology images really well.
That's a good way to put it. They hold promise for tackling complex predictions, like anticipating rare mutations or identifying subtle subtypes more effectively. The review mentions examples like models named Canon CH, UNI, Virchow, and Prov Gigapath.
So instead of building a new AI from the ground up for every single problem, you start with this giant pre-trained brain that already understands the fundamentals of histology images.
That's essentially the concept. It's like having a highly educated base model that just needs a little specialized training for a new area. And this ties into another related idea, generalist models.
Generalist, as opposed to highly specialized for one task.
Exactly. Generalist models aim to handle multiple tasks and maybe even multiple data types simultaneously within a single unified model. Imagine one AI system that could look at radiology scans, pathology slides, and genomic data for a patient altogether.
Integrated analysis.
Yes, and make a unified prediction or assessment rather than needing separate AI models for each data modality. It's about leveraging the synergy between different data types for a more holistic view of the patient's disease. Early studies are showing promise here.
And combining that multi-data approach with language capabilities.
That's the concept starting to emerge as generalist medical AI, or GMAI. By combining these powerful generalist models with natural language processing, the AI could potentially not only perform complex analyses, but also explain its findings and predictions in a way that's understandable and useful to clinicians, maybe even patients.
Like the large language models generating human-readable text now, but for medical data.
Kind of like that, yeah. Explaining the why behind its conclusions.
So the future's about bigger, more versatile models, handling multiple data types in concert, and maybe even explaining themselves better.
That seems to be a key direction, yes. Multimodal data fusion techniques, integrating pathology with genomics, proteomics, clinical records, radiology that's going to become increasingly sophisticated, providing that comprehensive view that's really essential for truly personalized medicine.
What challenges still loom large for that future? Are they the same ones we face now?
Many are the same, yes. Access to large, diverse, and well-annotated data sets remains absolutely critical, especially for multimodal approaches. And the review raises a really important point about equity.
How so?
Well, if the training data is primarily sourced from common cancers or specific demographic populations, there's a real risk that patients with rarer cancers or those from underrepresented groups might not benefit from these powerful AI tools as much, simply because the AI hasn't seen enough examples like theirs.
A digital divide in AI benefits.
Potentially, yeah. So strategies like collaborative data sharing across institutions may be generating realistic synthetic data and leveraging techniques like transfer learning or semi-supervised learning. They're all going to be vital to address this equity concern.
And the issues of trust and regulation won't just disappear with better tech, presumably.
Not at all. Developing truly explainable AI where clinicians can understand, or at least interrogate, why a model made a certain prediction is going to be essential for building trust. Regulatory and ethical frameworks need to evolve rapidly to keep pace with the technology, ensuring there are clear guidelines for validation, safe deployment, data privacy, and model maintenance.
Because the models might need updates as medicine changes.
Exactly. We need ways to ensure models stay current and don't become outdated or unsafe as medical knowledge and practices change over time.
And ultimately, getting these advanced tools into routine care still comes back to proving their worth in real-world scenarios, right?
Yeah, absolutely. Integrating AI evaluation directly into prospective clinical trials is necessary for that rigorous validation we talked about. These AI tools could even potentially serve as companion diagnostics for new therapies, identifying the patients most likely to respond before treatment starts.
Lots of potential there.
But building that trust among clinicians, demonstrating consistently that these tools are reliable, helpful aids, not replacements, but aids is paramount for successful integration into daily practice.
Okay. So we've taken a deep dive into how AI is rapidly moving through cancer pathology. We've seen how it's helping spot tumors and classify them more accurately, how it's identifying molecular biomarkers even incredibly, predicting genetic changes and patient outcomes just from looking at tissue images.
Yeah, and how all of that gets potentially even more powerful when you start bringing in other data types, that multimodal approach.
We've also navigated the significant hurdles, though. The cultural acceptance, the technical consistency needed, the critical demand for high-level clinical validation, and the ongoing need to adapt regulatory pathways and financial models for this new tech.
Absolutely. Those barriers are real and need continued focus.
And the future is definitely pushing towards these incredibly powerful foundation models and generalist AI systems that could provide a much more integrated, comprehensive view of a patient's cancer, potentially unlocking entirely new biological insights along the way.
It really feels like the application of AI is genuinely poised to reshape cancer care, ushering in an era of more precise, more efficient, and potentially more effective diagnostics and ultimately more personalized treatment strategies.
It certainly seems that way. But here's maybe a final thought to leave you with. If these powerful AI models can look at standard pathology slides, the same ones we've used for a century, and learn to identify subtle features that are invisible to the human eye, features that correlate with everything from underlying genetic mutations to long-term patient survival, what other layers of biological information might be encoded in the microscopic appearance of our tissues that we just haven't had the tools or maybe the perspective to decipher until now? What else is hidden in plain sight?